Welcome back to this series on topology. In today's video, we'll be discussing path-connectedness, which is another way of expressing what it means for a space to be connected that is stronger than the connectedness we saw in the last video. You can find a playlist containing all the videos in this series by clicking on the info thing that should appear right now. If you enjoy this video, please consider clicking the like button so that other people can find it more easily. So if we're given a space that looks something like the thing I'm drawing here, which consists of these two parts, we saw last time that one way of expressing that this space is not connected is by saying that we can decompose it into two non-empty, disjoint open subsets. And that was the content of the definition of being disconnected we saw in the last video. We then went on to say that a space is connected if it cannot be disconnected in this way by two non-empty open disjoint subsets. In this video, we'll approach the problem of connectedness in a different way, which will lead to the definition of path-connectedness. The main idea here is to look at paths between points in our space and use this to say whether a space is connected or not. For example, in this component here, I have some point, call it R, and some point P, and I can find a path going from R to P that stays within this component. On the other hand, if I look at a point Q over here, then it is not possible to find a path that goes from P to Q, which stays within the space. So any path that I draw will have to leave the space in order for it to go from P to Q. So we could say that the point P is not connected to Q by a path, and therefore this entire space is not path connected. So there's no path here going from P to Q that stays within the space. On the other hand, if we just restrict this component here on the left, then any 2 points in this component can be connected by a path. So this thing, if we just consider it in isolation, would be path connected. Let's now make these ideas precise. So first we start by defining what we mean by a path. For this, we let X be a topological space, and we let P and Q be 2 points in X. Now a path in X from P to Q is just a continuous map going from the unit interval 0, 1 into X such that f of 0 is the point P and f of 1 is the point Q. In other words, a path in X from P to Q is just a mapping of the unit interval into X such that the left endpoint 0 of the unit interval is mapped to P and the right one is mapped to Q. In pictures, if this is our space X, and we have a point P in this space and a point Q, then a path from P to Q is a continuous function from the unit interval. So this is the unit interval 0, 1 here. So we need to map this into our space X such that 0 gets mapped to P, and 1 gets mapped to Q, and then the rest, so the middle part of the interval, can be mapped somehow, but it has to stay within X. So these arrows here are expressing our continuous map F, and it's important that this map be continuous, otherwise this thing here wouldn't necessarily look like a continuous path. We can now use paths to define path connectedness. We do this by calling a space X path connected if for any 2 points in X, there exists some path in X from P to Q. So this is just the intuitive idea I sketched before. If a space is path connected, it means that if we select any 2 points in that space, then we can find a path in between them. If you think about such a path as walking from P to Q inside the space, then being path connected means that regardless where you start, and regardless where you want to go, there's always a way to walk from your starting point to your chosen destination. We'll now see that basically all of the properties that hold for connected spaces also hold for path-connected spaces. Recall that we saw in the last video that one of the most important properties of being a connected space is that the image of a connected space under a continuous function is also connected. And in fact, the same holds if we replace the property of being connected with the property of being path connected. So every continuous image of a path connected space is also path connected. Why is this the case? Well, suppose we have X be a path-connected space, and we have some continuous map F going from X to Y. Now our goal is to show that the image f of x is path-connected. Remember that being path-connected means that if you choose two arbitrary points in your space, you can always find a path that goes between those points. So we let P and Q be elements of this image f of x. And our task is now to find a path going between P and Q. To see how to do this, I'll draw a picture. So we have our space Y here, then we have our space X here, and the image of X is some subspace of Y. So this is f of x. I've now chosen some arbitrary points P and Q in the image. Now the information we have is that X is path-connected. So somehow we have to come up with a way of transporting a path in X to a path in Y that connects P to Q. And the obvious thing to do here is to look at the pre-image of these 2 points under this continuous map F. So up top here I have the pre-image of the point P, and on the bottom is the pre-image of the point Q. And now because X is path-connected, if I take any point in the pre-image of P and any point in the pre-image of Q, there will be a path going between them. So concretely, this means that there's a continuous map going from the unit interval to X that maps 1 to this point I've chosen in the pre-image of Q, and 0 to this point I've chosen in the pre-image of P. So the white arrows here, these are F, and this yellow stuff is gamma, which is going to be the path going from this point in the pre-image of P to the point in the pre-image of Q. And you can now see if I compose gamma with F, then this point in the pre-image of P will be mapped to P, and the point in the pre-image of Q will be mapped to Q, and the rest of the path will be mapped to something in the space f of x. And this is the path that we're looking for. Okay, so let's write this down formally. So I've taken some x in the pre-image of P and some y in the pre-image of Q. Now since x is path-connected, we can find a path gamma going from the unit interval to x, and this satisfies that gamma of 0 is equal to this point small x, which is in the pre-image of P, and gamma of 1 is equal to y, which is the point in the pre-image of Q. Now if we compose f with gamma, this is a function that goes from the unit interval into the space y, and even more particularly, it goes into the image f of x. And what does it satisfy? Well, it satisfies f after gamma of 0. Well, this is the same as f of x, which by definition, the way we've chosen x in the pre-image of P is P. And similarly, f after gamma of 1, this is f of y, and this is Q. So it satisfies these conditions that the endpoints are mapped to the right place. The only other thing we need for it to be a path is that this composition be a continuous function, which it is because f is a continuous function and gamma is a continuous function, and therefore their composition is also continuous. So in any case, this shows that f after gamma is a path going from P to Q. And I'll be using this sort of squiggly arrow notation to denote a path going from some starting point to some endpoint. Okay, so this proves this property. And I hope it also illustrates that proving things are path-connected is a lot more intuitive than proving things are connected. In the case of being connected, we always had to assume, for the sake of contradiction, that something was disconnected and then come up with a contradiction. And usually this involved messing around with these open sets and so on. And here, in this case, we can just compose two functions in a way that is completely intuitive. The next property is something we also saw for connected spaces, and it turns out that it also holds for path-connectedness. So let B alpha be a collection of path-connected subspaces of some space X that have a point in common. Then the union of all these B alphas is also path-connected. Again, it'll turn out that the proof here for the path-connected version of this property is much more intuitive than the one for the connectedness property. For the proof, we first call the point that all these spaces have in common P. So this is some point in the intersection of all these B alpha. We now want to show that the union of all the B alphas is path connected, which means we need to take two arbitrary points in the union and find a path between them. So we take some X and Y in the union of these B alphas. So then X is in some B alpha and Y is in some B alpha prime for alpha and alpha prime in this index set A. That just follows from the definition of the union. If you have a point in the union, then it has to be in one of the sets that we're unioning over. Okay, here's where the path connectedness of these spaces B alpha comes in. So since B alpha is path connected, we have some path gamma which goes from this point X to the common point P, which lies in all of the B alphas. And since B alpha prime is also path connected, we have a path, which I'll call gamma prime, which goes from this point P, which lies in all the B alphas, to Y. And well, now you see what we would like to do. We would like to first do the path gamma going from X to P, and then do the path gamma prime from P to Y to get a path going from X to Y. So I'll write down how this operation works first in the picture. So we have the unit interval here, and we have a second unit interval here for each of the paths. Then we have our union of the B alphas, so this big space here, with this common point P happening here. Then our point Y is up here, and our point X is down here. Now gamma is a path from X to P. So this is gamma. And gamma prime is a path going from P to Y. And we'd now like to first take the path from X to P, and then take the path from P to Y. So essentially what we'd like to do is we'd like to glue these two intervals here together, and then just go from here all the way up to here, and map that to this path in the space union of the B alphas. To get such a composite path, we need to map out of the unit interval in such a way that 0 gets mapped to X and 1 gets mapped to Y. And the way to do this is to split this unit interval here on the very left in blue into 2 bits and map 1 bit to the bottom unit interval that is the domain of gamma, and then map the other bit to the top unit interval, which is the domain of gamma prime. So here this is gamma prime. Okay, so we just split the unit interval in half. And now we map 0 to 0 and map 1/2 to 1. And in the middle here, we just extend linearly. Then once we're strictly greater than 1/2, we map into the second interval here so that we're in the domain of gamma prime, and then we compose with gamma prime. Okay, so the idea is basically we start here at 0, then we move up until 1/2, and in this area we're basically just doing the movement over here, and this will produce this path in our space union of the B alphas. And once we're over 1/2, we move over to this interval and then produce this path. Now, it doesn't really matter so much how we map this big unit interval here to these smaller ones, but it's pretty easy to just do it linearly. And if we write all of this down formally, we get the following definition. I'm going to call this composite path I'm trying to define, I'm going to call it gamma star gamma prime. So this is saying that we first want to do the path gamma and then do the path gamma prime. And this has to again be a function that's continuous, going from the unit interval to our target space, which in this case is this union of the B alphas. And how does it work? Well, it takes a t in the unit interval and maps it into one of two cases depending on the magnitude of t. If our t is between 0 and 1/2, we want to be using gamma. However, we want to use gamma at double speed because at the point where we're at 1/2 in the unit interval in blue here, we want to be at 1 in this yellow interval. So we use gamma at twice speed if t is between 0 and 1/2. And if t is greater than 1/2, but less than 1, we want to be using gamma prime. And again, we want to use gamma prime at twice speed because here we only have 1/2 length, and here we have 1 whole length. So it's again going to be gamma prime of 2t. However, we start our journey here with some value that's a bit bigger than 1/2, and we want this to be mapped to 0. So if we multiply 1/2 by 2, we get 1, so we have to subtract 1 inside here in order to make things work out. So you can now check that if you plug in 1/2 here, you get 0, and if you plug in 1 here, you get 1, which is exactly the domain that gamma prime has. Okay, so this is a general phenomenon. If we have two paths, so we have some path going from x to p and some path going from p to y, then we can form their composite as paths, which means we can first do the first path gamma and then do the second path gamma prime. And if we define it in this way, then it results in a path that goes from the starting point of the first path to the end point of the second path and uses the common intermediate point as the place where it connects. Okay, so with this, we've defined a new path, this gamma, then gamma prime, and, well, we only use these continuous operations when defining it. So this definition here defines a continuous function going from the unit interval into this space we're interested in. And if we plug in 0, we're up in this case and get gamma of 0, which is x, because gamma is a path from x to p. And if we plug in 1, we're in this case down here, and in that case we get gamma prime of 1, which is y. So this thing is indeed a path going from x to y, and this proves this property because we chose two arbitrary points in our space we were trying to prove is path connected, and we showed that we can construct a path between them. All right, so perhaps in this case, it's maybe less important to precisely remember the statement and more important to remember that we can perform this composition operation on paths because that's more useful in general. And if you remember how this works, then it's immediately obvious that this statement is correct. Our next property is, again, something we saw for connected spaces, which also works for path-connected spaces, namely that if we take a finite product of path-connected spaces, then the result is again path-connected. By induction, we can reduce to the case where we just look at the product of two path-connected spaces because we can just iterate that a finite number of times. So we let x and y be path-connected. And, well, we want to show that their product is path-connected. So we take some x comma y in x times y. And we also take some x prime, y prime in x times y. So these are 2 points in the product that we choose arbitrarily. And now we want to show that there's a path between them. Again, there's not a whole lot we can do except use our hypotheses. So we know that since x is path connected, we have some path gamma, which goes from x to x prime. And similarly, since y is path connected, we have some path theta going from y to y prime. So let's again draw a picture. So we have our space x here and our space y here. We have a path going from small x to small x prime, and a path going from y to y prime. So this means that we're mapping this unit interval here once up to x to get a path. So this is gamma. And then once to y to get a path. This is theta. And now we want to use these two maps to construct a path in the product space x times y from x comma y to x prime comma y prime. Now the way to do it in this case is just to define this new path component-wise. So the abstract way to think about this is that whenever you have a pair of continuous maps going from a common domain into two spaces, then by the universal property of the product space, you get a continuous map going from that common domain into the product space. So what we'll get here is a map going from the unit interval into the product space, and this map could be denoted gamma times theta. And since this is the most natural thing we could do in this situation, it's not surprising that this will turn out to have the right properties to be a path going from this tuple x comma y to x prime comma y prime. All right, so how is this product map defined? Well, gamma times theta of some t, well, this is just applying each of these maps component-wise. So it's going to be the tuple gamma of t comma theta of t. So if you remember from the video on product spaces, the way to prove this universal property is to explicitly construct this map here and show that it satisfies this universal property, and the way you construct it is by this definition. Okay, so if we make this definition, well then gamma times theta is a map from the unit interval into x times y, and moreover it's continuous because each of these guys is continuous. That's something we saw in the video on product spaces. If you have two continuous maps and you take their product in this way, the result is again a continuous map into the product space. And finally, we need to check that the endpoints are mapped to the correct destination and source. So we have that gamma times theta of 0. What's this? Well, it's just gamma of 0 comma theta of 0. And well, gamma of 0 was x, and theta of 0 was y. So indeed, 0 is mapped to the point x comma y. And similarly, gamma times theta of 1 is equal to gamma of 1 comma theta of 1. And well, gamma of 1 is x prime and theta of 1 is y prime. So the point 1 is mapped to x prime y prime by gamma times theta. Okay, so this shows that if we take two arbitrary points in the product, then we can construct a path between them by taking a product of paths in the factors. So here again, you see that working with path connectedness is much easier than working with connectedness, essentially because we're dealing just with continuous functions, and we have all of these tools for working with continuous functions, such as these universal properties for product spaces. Okay, and now the final property is also something we saw for connectedness, namely that every quotient of a path-connected space is also path-connected. And well, the proof is exactly the same as it was for the connectedness property here, because the only thing we're using is that if we have a quotient, then we have a surjective map from the space that we're quotienting to the quotient space. And well, if that original space was path-connected, then the image of that space is the entire quotient space under a continuous map, and this will also be path-connected by property A we saw in the beginning. Okay, so let Q be a quotient of some space X. So we have this quotient map Q going from X to the quotient, and this is surjective and continuous. So by surjectivity, we have that Q is equal to the image of X under this quotient map. And we know that this thing here is path connected because X is path connected by property A. Therefore, Q is path connected, and that proves this property. So this isn't really anything new, but it's just restating an easy consequence of property A. But because quotients are so important, it's really important to keep this property in mind. Okay, so we've defined path connectedness, and we've seen that basically the same properties that hold for connected spaces also hold for path connected spaces. So a natural question is to ask how these two things, path connectedness and connectedness, are related. Because if they would turn out to be equivalent, really it doesn't make sense to study both of them, right? We could just study one of these things. Now it turns out that path connectedness implies connectedness, but not the other way around in general. Now, the fact that path connectedness is stronger than connectedness is actually a good thing, because working with path connectedness is easier. And so if you prove path connectedness, you automatically prove connectedness. So in many cases, you can prove path connectedness, and this will show in particular that your space is also connected. And in fact, there are very few nice spaces that are connected but not path connected. So in most cases, you can just work with path connectedness all the time. In particular, if your space is a manifold, then these two things are equivalent, so we can just stick to focusing on path connectedness. The proof of this theorem will turn out to be surprisingly simple, but it will rely on the fact that we proved that the intervals on the real line are connected. And if you recall, in the last video, we had to put in a lot of effort to show that. So this is one of those instances where we're reaping the benefits of all the hard work we put in to prove that intervals are connected. Okay, so we want to prove that path connectedness implies connectedness, so we let X be a path connected space. Now the idea will be to express X as a union of paths which, because they're images of the unit interval under continuous functions, are connected. Recall from the last video that if we have a collection of connected spaces that share a point in common, and we take their union, then the result will also be connected. Therefore, we have to ensure that these paths in X have some common point, and this is why we are going to fix some point P in X. Now, since X is path connected, we have for any small x in X, there exists some path gamma x going from P to X. Moreover, if we look at the image of the unit interval under this path, so we're just looking at the path sitting inside the space X, this is connected because on the one hand, the unit interval is connected, as we saw in the previous video, and because gamma x is continuous. And we know that the continuous image of connected spaces is again connected. We can now write X to be the union over all small x in X of these images of the unit interval under gamma x. So why does this equality hold? Well, on the one hand, if you take any point in X, then this is the endpoint of one of these paths, gamma x. Therefore, any point in X will be contained in this union. On the other hand, any one of these images, gamma x of the unit interval, is contained in X, and therefore the union of all of them will also be contained in X, and this establishes this equality. So maybe a picture helps here. If our space X looks like so, and we have this point P here, and well, we're taking any point in X, and we're looking at this path going from P to X, and so this orange line here is what I'm denoting gamma X of the unit interval. And now if you union together all of the paths of this type for any point in the space X, well, then you'll recover the entire space. So we've now written X as this union, and well, this union is, well, it's a union of connected spaces which all contain the point P. And therefore, by a property we saw in the previous video on connectedness, this implies that this union is connected. But this union is just X, so X is connected. And this proves the theorem. So as I said, it's surprisingly simple once you know what you need to do. But again, a lot of hard work is hidden in this fact here that the unit interval is connected. Okay, so this establishes that path connectedness is stronger than connectedness. In particular, if we can show that a space is path connected, which tends to be easier, then it also shows that the space is connected. And now with this tool in hand, we can come up with a bunch of examples of connected spaces, which was difficult to do before. Okay, so the following spaces are path connected, and hence in particular they're also connected. So the first example of a path connected space is Rn. Why is this? Well, Rn is the finite product of copies of the real line. So this is just R times R and so on, n times. And it's pretty easy to see that R is path connected. So if we think about the real line and we take any 2 points on the real line, P and Q, well, we can get a path between them by just mapping the unit interval linearly to these points in between. So in pictures, if this is our unit interval, then we would just map 0 to P, 1 to Q, and any point in between we would linearly map to points in between P and Q. So if we had to write this out, we would have a function gamma of T, which is equal to, well, on the one hand, we want it to be equal to P when it's 0, so we'll put 1 minus T times P here, and then we'll add T times Q here, so that it's Q when T is equal to 1, and then all the points in between will be covered. Now, since we're just using addition and multiplication here, this is a continuous function, and if you plug in 0, you get back P, and if you plug in 1, then this term vanishes, and then you get back Q. So this is indeed a path from P to Q. All right, so that establishes that one copy of the real numbers is path connected, and we saw that finite products of path connected spaces are again path connected, so if we take the product n times the real line, then that space will be path connected as well. The next example of path connected spaces are convex subsets of Rn. What does that mean? Well, a convex subset is a set such that when you take any 2 points in that subset, then there's a line that goes between them that stays within the subset. So the thing I drew here is almost convex. There's maybe a little bit of an issue here. You might be able to take these 2 points and not be able to connect them with a straight line, but let's just assume that this is a convex set. An example of a non-convex set would be something like this moon shape. Here we could take these 2 points, and these are not connected by a straight line which stays within the subset. This definition extends to arbitrary dimensions, so you can do the same thing with vectors, and there it's then easy to see that convex subsets are path-connected because this line going between the points that stays within the set, this gives you a path between any 2 points. In fact, the path looks exactly like the path I've defined here, just instead of using points P and Q that are real numbers, you would use vectors. Okay, so the next example is the sphere, the n-sphere Sn, for n greater or equal to 1. So recall that for n equals 0, the n-sphere is the disjoint union of 2 points, so that would not be path-connected. However, as soon as n is at least 1, then the n-sphere is path-connected. Maybe I'll illustrate this for n equals 2, so in that case we actually have a sphere. If I take any 2 points on the sphere, then I can define an arc that goes between them and that remains on the surface of the sphere. If you actually wanted to write out this arc, you would probably do it in terms of sine and cosine functions, so you would parameterize this sphere in terms of sines and cosines, and then you would come up with a way to map the unit interval to this arc using sines and cosines. Doing that essentially amounts to thinking in polar coordinates, and you would then keep the radius of your polar coordinate constant along this path, so it's always radius 1, and you would just vary the angles between your vector and the various axes in some linear fashion, for example. Now, writing down this map properly will bring us too far off course, but it's pretty intuitive to see that the circle S1 and the sphere S2 need to be path-connected. Finally, again using the property that finite products of path-connected spaces are path-connected, it turns out that the torus, so the n-torus, which is n copies of S1, is also path-connected because S1 is path-connected. So this already gives us a bunch of examples of path-connected spaces and hence connected spaces, and we can generate more connected spaces by, for example, mapping these existing spaces continuously into other spaces and looking at images there. Or we can also generate new connected spaces from these examples by taking quotients. Okay, so we saw that path-connectedness implies connectedness, but I claimed that the other direction of implication does not hold. To prove that that's the case, we need to come up with a space that is connected but fails to be path-connected. The standard example for this is called the topologist's sine curve, and it's defined in the following way. So I've drawn a picture of it down here, so you can follow along. So we start by defining a set T0, which is all the points xy that have x-coordinate 0, and where y lies in this interval from -1 to 1. So that's this red bit here I've drawn in the picture. And then we define a second set, t+, which is essentially the graph of sine of 1 over x. So here it's all the points xy in the plane, such that x lies in this half-open interval from 0 to 2 pi, and y is equal to sine of 1 over x. So this curve will start at some point, and then it will oscillate, and the oscillations will always get quicker as it approaches 0, because in that case, the argument here in the sine function increases towards infinity. Now the claim is that the union of these two subsets, so T0 union T+, which is what I've drawn down here, is a connected space, but not path-connected, and here we're viewing this subset with a subspace topology in R2. So I'm not going to prove this in detail. You can think of this as an exercise and ponder it for yourself, but I'll just sort of sketch the intuition for why this is the case. To see that T is connected, we can observe that both T0 and T+ are individually connected spaces. Why is this? Well, for example, because each of them is path-connected. And we saw in the video on connectedness that connected sets have the following property, namely if you have some two disjoint sets in the larger space, then the connected subspace has to lie completely within one of the sets. So in particular, if I try to find two sets which disconnect the space T, T0 will have to lie completely within one of them. So this means that one of the disconnecting sets has to be an open set which contains this set T0. But now, because this open set is an open set in the subspace topology, it's the intersection of some open set in the plane with the space T. Now, open sets in the plane have the property that if you take any point within them, there exists a small open ball lying completely within the open set. In particular, if I take any point here lying in T0, there needs to be a small open ball around it that still lies completely within this pink set, and, well, therefore also whatever part this open ball intersects with T+, so the part it intersects with the blue curve, needs to lie within this open set, which is supposed to be one of the disconnecting sets. All right, but now since T+ is connected, and it has some point which lies in this pink disconnecting set, we know that the entirety of T+ needs to lie within the pink set. Therefore, we've shown that both T0 and T+ both need to lie in one of these disconnecting sets, which means that the other disconnecting set is empty, and in fact we didn't have a proper disconnection of the space. So that argument proves that T is connected. Next, I'll sketch why T is not path-connected. The reason for this is that there are 2 points in T, for example this point here, which I'll call P, and this point up here, which is the point 0, 1, which cannot be connected by a path. Intuitively, this is the case because any path that starts at P has to follow along this graph of sine 1 over x, and well, this graph starts oscillating wildly here, and it basically never reaches this point 0, 1. Or another way of saying this is that the limit of this function as x goes to 0 is not defined, but on the other hand, it somehow has to be 0, 1 if we want such a path. So this whole argument was very sketchy and maybe not entirely precise, but it contains the main idea about how you would go about proving this. All right, so let's summarize what we saw today. So we started off by defining the property of path-connectedness, which is very intuitive. The space is path-connected if for any 2 points in the space you have a path going between them. We then saw that many of the properties of connected spaces also hold for path-connected spaces, and in fact, path-connectedness implies connectedness and is often easier to work with. However, the converse does not hold, so there are connected spaces which are not path-connected, the standard example being this topologist sine curve, but these spaces are sort of strange in the grand scheme of things, and for many nice spaces, path-connectedness and connectedness actually turn out to be equivalent, which means that in these nice spaces we can just work with paths and forget about all the connectedness stuff. In the next video, we'll continue looking at connectedness. In particular, we'll see what path components and connected components of a space are, and we'll also see local versions of these connectedness properties.